Greetings. My name is Bill Skamrock, and I am going to discuss how the atmospheric component of Empath integrates in time the equations of motion that underlie the model. We're going to discuss first the algorithms that are used, and then point out the time steps, and from a practical point of view, where those time steps are set in the namelist.atmosphere that is used to configure the Empath time integration. And finally, there'll be a few references for those of you who are interested in more details concerning the time integration and how it was developed. The equations of motion are presented here on this slide, and essentially there are 5 canonical equations. There's one for the horizontal momentum, there's one for the vertical momentum, there's an equation for the potential temperature that's multiplied by density, there's the continuity equation, i.e. the equation for density, and then finally there are time rate of change equations for all the constituents that are composed the atmosphere outside of the dry air density. And that includes moisture, chemical species, aerosols, etc. Anything else that's being transported in the model. And anything else that is needed by the model to integrate the equations have what are called diagnostic relations. So as you can see, there's not an equation to integrate forward in time the pressure. The pressure is diagnosed from the state variables that we do integrate forward in time. What we are going to concern ourselves with in this presentation is how we do the time integration. How do we integrate forward in time those prognostic variables which the model is predicting? The primary time integration in Empaths is based on a Runge-Kutta scheme. Now, there's essentially an infinite number of Runge-Kutta schemes, and they're used to integrate ordinary differential equations or as part of systems of equations, of partial differential equations, for example, here in the atmospheric model. And these Runge-Kutta schemes concern themselves with how to integrate the time rate of change of a variable. So remember from the last slide that the time rate of change of a variable, which is sitting here, is just a derivative with respect to time of a prognostic variable, which we're integrating forward in time. So the Runge-Kutta scheme says, how do I integrate this term in time? And there's essentially, we are trying to take a step forward in time, and that time step is delta t here. And the Runge-Kutta scheme, the third order variant that we use, is as follows. First, it takes the solution at time t, and then takes all the other terms that are not the time rate of change and evaluates them using that time t solution, and takes a third of a time step, delta t over 3, to produce this first predictor, phi star. And phi is a generic variable that we're stepping forward in time. The second part of the Runge-Kutta step is to take that predictor, nominally at the third delta t time level. We reevaluate all these other terms on the right-hand side, and then we start again at time t, and then take a step to the halfway point of the time step, delta t over 2. And that gives us yet another predictor, this phi star star, superscript star star. And then we evaluate the right-hand side terms once again using that latest predictor, and then we take the full time step to time t plus delta t. That is the third order time integration scheme that is used in Empath-Atmosphere. If you look at the oscillation equation, where I is the square root of -1, if we look at just the oscillation equation, it should essentially, the amplitude of the solution should not change. It should just propagate forward in time with that same amplitude. This is just a wave equation. The waves should not grow, nor should they decay either. So the absolute solution says this amplification factor A between time steps should just be 1. And this third order Runge-Kutta scheme gives us an amplification factor of 1 minus the frequency times delta t to the 4th over 24, plus higher order terms, meaning delta t to the higher power than 4. What this is telling us is that this is a third order scheme, It gives you the correct solution through k delta t cubed. And it also tells us, given this is a negative sign here, that the solution decays. So the scheme is stable. The solution will just slowly decay in time. Whereas if this had been a positive term, that would tell us that the solution is growing in time, and this type of formulation would be unbounded and would be an unstable scheme. So we like this because it's quite accurate. It's fourth order accurate in time for linear systems, as we've looked at, and it also produces decaying solutions. So we like this scheme, and that's why we use it in Empaths, and it's used, for example, in Wharf and some other models. Now, you also have an option in Empaths, and it turns out it's the default in Empaths, to use a second order variant of this scheme, where instead of stepping to delta t over 3 for that first predictor, one steps forward to delta t over 2. And that has an error term again with a minus sign, leading to the minus sign, 1 minus. But now this is delta t cubed, the first error term you see. So it's a second order scheme. It's accurate through a delta t squared in terms of the Taylor expansion of the scheme for the oscillation equation. This is what's used in Empath for the default. You can change it to go back to the third order scheme. Now, if you look at the stability analysis of these two schemes, it's depicted as so. On the vertical axis, the y-axis here, we're plotting the amplitude of this coefficient A for this equation. And this k delta t, which is part of the solution expansion, is on the x-axis here. And what you see for the third order scheme is the amplitude goes above 1 for the response for k delta t greater than 1.73. And that means for time steps that would make this quantity where k would be the highest frequency mode in the discrete system, means delta t that has this product higher than 1.73, the solution will go unstable. The second order variant, you can see, you can take a slightly larger delta t before the amplitude goes above 1. That's why we've implemented this in Empath as the default. And what we see in applications is that there's very little difference between those two solutions. We do not see anything we can point to which suggests that the accuracy is compromised. Stated another way, we believe that the errors in the solution are dominated by the spatial discretization and by the physics and not the time integration. Hence, we can use a somewhat less accurate time integration that allows us to use somewhat larger time steps. The Runge-Kutta time integration is used to integrate the meteorologically significant modes, what we call the slow modes. These are most of the gravity waves, the transport of these waves by the wind speed, by the wind that's flowing, the Rossby waves. These are slower propagating modes that are integrated by that Runge-Kutta scheme. The non-hydrostatic equations also have sound waves in them, acoustic waves, and these propagate very quickly. They have high frequencies. The explicit Runge-Kutta scheme, if we handled the acoustic modes with that, would be severely limited in the time step we can take. So we integrate the acoustic modes with a much shorter time step that's stable for those fast propagating modes, while the rest of the terms in the equations that are not responsible for acoustic modes are integrated with that Runge-Kutta scheme over a longer time step. This is called a split-explicit time integration. It's very common in non-hydrostatic models of the atmosphere, and it's been around since the early 70s. So the basic approach has been around for a long time, and it's very well tested. The Runge-Kutta time integration using this split-explicit approach with the smaller time step for the acoustic modes came about in the early 2000s because the accuracy of the Runge-Kutta and its ability to handle different ways to integrate the slow modes within the time integration was very beneficial to the models we've been constructing, and hence the time splitting you see here is about 20 years old in terms of its genesis and where it was developed. Now, the split-explicit scheme handles stably the horizontally propagating acoustic modes. Acoustic modes also propagate vertically, and the grid spacing in the vertical is much, much finer than the grid spacing in horizontal. Hence, if we were to handle explicitly the vertical propagation of acoustic modes, it would provide a severe restraint on the smaller time steps we're taking for the horizontal propagating acoustic modes. So what we do vertically is we integrate the acoustic modes implicitly. Because vertically it's just in the column, the elliptic equation that results from that vertical integration of the acoustic modes is very easily solved. It's a tri-diagonal system, and it's a simple inversion. Again, that's also part of the split-explicit time integration technique that was developed in the 70s. So all of this technology is fairly well known, well understood, well analyzed, and has been used for a long time in models. So that is another time step that you can set within MPAS. It's acoustic time step, or the small time step as we sometimes call it. Here depicted on this slide is pseudocode, which indicates how the different time steps in the model are used to integrate the prognostic variables forward in time. The first set of loops here over these do dynamics split steps integrates what we consider the dry dynamics forward in time. And the dry dynamics include the transport of momentum, potential temperature, and dry air density. In addition to embedded in that, of course, are acoustic modes, gravity waves, Rossby waves. That's followed by an integration of the scalar variables down below here, such as, for example, the moisture species, water vapor, rainwater, cloud water, chemical species, aerosols, anything else that needs to be transported by the model is transported in this lower loop down here. So, if we look at the dynamic step, what we're doing is we're taking some number of Runge-Kutta steps to equal one transport step, and we'll get to those time steps in a few slides. But each dynamic step is a Runge-Kutta integration, and that Runge-Kutta has three substeps as depicted here from the previous slide, how the acoustic steps are integrated. First, of course, the right-hand sides are evaluated. The slow mode time tendency is evaluated. All the terms are going to keep fixed over the acoustic steps. Then we drop into an acoustic step loop that takes smaller time steps that are stable for the acoustic modes. It turns out on this first part of the Runge-Kutta step, we just take the full step because it's not necessary that it be small, such as being stable for the acoustic modes here in the full step. But the subsequent middle Runge-Kutta step, number 2 here and number 3, these time steps here, these acoustic steps depicted by these arrows, these black line with the arrows at the end, these are set to be stable for the horizontally propagating acoustic modes. And as I mentioned in the previous slide, the vertically propagating acoustic modes are handled implicitly, so they do not restrict time step. So that is how that's worked. And as mentioned, those acoustic steps here, as you can see, are those substeps over which the solution's actually advanced. And the reason it's Runge-Kutta for the slow modes is that this slow time step tendency, which involves most of the terms in the equations of motion that I showed you, they're held fixed over these acoustic steps, so they're not updated. Only the terms, the critical terms that are crucial for integrating the acoustic modes are updated each of these small time steps. So that is the split-explicit time integration for the dry dynamics. Now, below that is the time integration scheme for the scalars here. And that's just a straight Runge-Kutta integration. There are no substeps. involving the acoustic modes because moisture, chemical species, etc., they are acoustically unimportant. They really do not affect in any significant way the acoustic modes, and so we just handle them with a straight Runge-Kutta time integration to accomplish their transport. The nice thing about this kind of splitting is, first, looking at the scalar transport here, we can use any scheme we want here. Right now, we're using Runge-Kutta, but we can use other schemes if we so desired. And in the future, we're looking at potentially using other schemes within Empaths in this regard, although we think the Runge-Kutta time integration is actually fairly accurate and quite robust in this application here. So we're sticking with it for now. If we look at the dynamics time step, as you can see, we split the dynamic step into a number of substeps to equal the time step here for the scalar transport, because we find that the stability of the model really is dependent upon the stability and robustness of the integration of the acoustic and gravity wave modes associated with the dry dynamics, and that tends to be more tightly constrained than just scalar transport. So we take a number of dynamic steps for each scalar transport step, because the stability of this is more severely limited in that time split approach than that of the scalar transport. The configuration of MPAS-Atmosphere for time integration to produce forecast is controlled by parameters set in the namelist.atmosphere file. Inside that name list, there are several sections, and the first section you come across is the section, this NYHD_model, it's non-hydrostatic model. And inside of it, you'll find a number of configuration parameters that are all preceded by config_something. The first one you see typically is DT, and this is the time step in seconds, and we'll talk about how to set that later. But there are three other parameters that control how the integration occurs in the time step itself. And those three parameters are, first is config split dynamics transport, and the default is true. And what that means is that the dynamics, the first main loop to the left here, is integrated separately from the transport of scalar species, the moisture and everything else. That's the second part in that loop. So they're integrated sequentially as opposed to together. The other two configuration parameters you'll find are the config dynamic split steps, and that's how many steps of each Runge-Kutta integration is needed to advance the dynamics to equal one scalar transport step, and the default for that is 3. And the second one is the config number of substeps, and those are acoustic substeps inside each dynamic substep. And here we set that equal to 2. That's the default. So these are all default settings that you'll see for a typical configuration for a real data simulation on the sphere using Empath. The time steps that those imply are given below. First, if you look at config dt, which we have equal to 90 seconds, and that's the time step in seconds right here for the scalar transport step. And that's a single step in the course of the main time step of the model. So when you set that config dt, what you're setting is the time step used by the scalar transport. And now the dynamic steps are going to be that scalar transport time step divided by the number of dynamic split steps. This is going to be the time step for each one of these Runge-Kutta integrations, each one here. And of course, the Runge-Kutta integration itself has 3 substeps. So that's what that will be. And the acoustic steps is just the fraction, or this integer number, config number of substeps, that divides the dynamic time step to give you each of those smaller acoustic steps. So that's the time steps you're setting when you set the main model time step and this config dynamic split steps and this config number of substeps here when the split dynamics transport is true. This is a depiction of the full time step for that default configuration. So what you're seeing here is first the dynamics time steps are happening. And remember, the default configuration uses time integration order 2. You won't typically see this in namelist.atmosphere. It's a hidden parameter. You can include this. You can edit the namelist.atmosphere file and include this and set this to 3, and then we go back to that third order variant. But the default is 2. And what happens in this default configuration is that there's 3 sets of Runge-Kutta time steps to integrate forward the dry dynamics for each scalar transport step. And within those 3, there's acoustic steps. There's the first part of the Runge-Kutta time step, the middle, which again goes to delta T over 2, and then the final step, which takes 2, to integrate each one of these Runge-Kutta time steps for the dry dynamics. When we finally get to here, we go down and then integrate the scalars forward in time to step forward in time their values. So this is the time step integration graphically presented for the default configuration of MPAS-A. And if you change those default values that are in there, what you're going to be doing is changing the time steps. If you just change DT, of course, everything just gets scaled by DT, and it looks exactly like this. This is for any generic DT. But if you change the number of acoustic steps, there'll be a different number in here. If you change the number of dynamic split steps, there might be 2 or there might be 4, or you can make those changes if you have reason to believe that the stability is problematic, or perhaps you want to take larger time steps in some subcomponent here, the time integration. You can do so by modifying those 3 parameters to change this time step, and the acoustic step. So you have access to all of those time steps. For only one is specified in terms of a physical time step in seconds, and every one is just some fraction of, so that's the main time step, and the other ones are just a fraction of that main time step. Now, many of you are probably familiar with the Wharf Model. The Wharf Model, while also using a split-explicit time integration, does not perform a split dynamics transport step. It doesn't split the transport from the integration of the dry dynamics. However, you can configure Empaths to do the same integration that the Wharf Model does, and that's by setting this config split dynamics transport step logical to false, and this is done here, and the time step integration you get is shown here, and here the Runge-Kutta step that integrates the dry dynamics also integrates the scalar transport at the same time. That's the difference between the split dynamics transport configuration of Empath versus the non-split dynamics transport configuration, that non-split one being then identical to Wharf time integration. And in that case, you've only got 2 time steps that you have access to. The main time step that you set in the model, this config DT, is just the time step of the dry dynamics because it's the same as the time step of the RK3 transport. And that acoustic step is just that config DT, which is the dynamics of scalar transport, delta T, divided by the number of substeps that sets the acoustic step. Again, the vertical is also integrated implicitly, so that time step is stable for all the vertically propagating modes. So if you choose to configure Empath with the same time integration scheme that's used in Warp, you can do so. The split dynamics transport option is much more robust, particularly in the global setting, and we recommend you stick with that. but we have the other option available if you want to go to the Wharf configuration of the time integration. To set the time step in MPAS, we actually typically use a similar estimation process as we use for Wharf. Similar to Wharf, we typically set that model time step in seconds. We begin with something that's approximately 6 times the finest mesh spacing, the cell center spacing on the MPAS mesh in kilometers. So for example, for the 15-kilometer MPAS mesh or the variable resolution mesh where the finest part of the mesh is nominally cell center distance of 15 kilometers, we would use a 90-second time step. For Wharf, this kind of rule of thumb is typically stable, but sometimes it's not. For MPAS, it almost is always stable. And oftentimes you can go, instead of a 90-second time step, you can even go a 120-second time step because of that split integration between scalars and dry dynamics. So that's something you can experiment with in MPAS. In terms of testing your configuration, so you set a time step and then you run the model. If you find out it becomes unstable very quickly, for example, after just a few time steps, it may be that the acoustic modes are unstable. And essentially to test whether that's the case, so if you push the time step a little bit and you find out it goes unstable and you think that that's probably could be suspicious, first you can reduce that to config DT and make sure it is stable in what we think should be a stable time step, following that rule of thumb. If it is stable, then you may want to increase the number of acoustic steps, and you can do that by increasing that integer config number of substeps, which divides the dynamic step to get the acoustic step. If you make that integer larger, that will decrease the acoustic step. It'll take more to get through those substeps of Runge-Kutta substeps in the dynamics. The only key thing here is that integer that you set has to be even, because we have to be able to integrate to the halfway point of the time step. So that's why we require that to be even, and there's a check to make sure it is in the model. So if you mess up, it'll tell you. You can also change the number of dynamic steps per scalar time step in the split scheme. Right now it's set to 3. You can make it larger than 3. You can actually make it smaller than 3, which would make the acoustic steps bigger, holding everything else constant. But if you make it, for example, 4, everything scales, so the acoustic steps will be smaller. So you can test that to see if that gives you stability by making it larger. If in experimenting with these time steps and making them smaller, the problem does not go away, you still see instability the first few time steps, and it's much more likely that there's a problem with the initial conditions in the model, how the physics are being initialized, something in the initial conditions file itself. So you need to check your initial conditions and other aspects of the configuration to see if there are any problems with those. There are references if you want to understand in more detail how these integration schemes work. For the Runge-Kutta scheme, in which we've placed our split-explicit time integration, you should look at this paper 2002 by Lou Wicker and me that talks about the splitting method for that third-order Runge-Kutta scheme, and it lays it out in a pretty straightforward way, and you'll get a good understanding of how, historically, why that is a scheme that we've now moved to. If you want to understand in a lot more detail, how the split-explicit integration for the acoustic modes work, then you want to go to the paper by Joe Klemp, myself, and Jimmy Dudia, the 2007 paper that explains in great detail how the acoustic modes are split off from the dry dynamics in the splitting scheme, including how the vertically propagating acoustic modes are integrated implicitly in the split-explicit time integration. So I strongly recommend you look at that if you want to understand in more detail how the MPAS model time integrates the equations of motion.